On April 6, 2026, 4 astronauts slipped behind the moon and lost all contact with Earth for 40 minutes. When they came back, they brought 7,000 photographs. And a problem. The moon is hiding something. It has mass where there shouldn't be any. It remembers a magnetism it lost 4 billion years ago. One hemisphere is smooth, the other is a battered wasteland 20 kilometers thicker. No one can fully explain why. Tonight, we descend into that mystery. If it pulls you in, hit subscribe and stay with us. Prepare yourselves. We begin. The spacecraft slipped into silence at 6:39 p.m. Eastern Time. No voices from Houston, no telemetry, no link back to Earth at all. 4 astronauts were inside: Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. Their capsule integrity was threading the narrow gap on the far side of the moon, the side that permanently faces away from us. And for 40 minutes, the moon itself cut them off from every human being who had ever lived. This was the plan. Mission Control had warned them. The moon blocks radio signals the way a mountain blocks a flashlight. Nothing gets through solid rock 2,000 miles thick. But for those 40 minutes, something else was true. 4 people were farther from Earth than any human had ever traveled. 2,000 miles. More than 4,000 miles past the record set by Apollo 13 in 1970. And the only thing between them and the vacuum of deep space was the moon. A moon that, it turns out, we barely understand. Imagine the silence inside the cabin. The only sound is the hum of the life support fans and your own breathing. You press your face to the small round window, and below you, filling the entire view, is a surface that no human eye has ever seen directly from this close. Not one. The Apollo astronauts glimpsed pieces of the far side. They never got this view. They never sat over it for 7 hours, cameras clicking, voices describing craters that had no names. Koch said something strange during that pass. She told Mission Control that the cratered surface looked like a lampshade with tiny pinprick holes. Glover radioed that the terrain had colors: brown, green, hints of texture that Earth-based telescopes had never resolved. That single observation should not have been possible. The moon, as every textbook tells you, is grey, dead grey, dust grey, ash grey, a monochrome wasteland. And yet the first 4 humans to see it up close in half a century said, it has color. What are we actually looking at? That question is the reason this story exists. Because the closer we get, the stranger the moon becomes. Gravity that tugs spacecraft off course for reasons scientists argued about for 60 years. Magnetic rocks on a world with no magnetic field. A far side with a crust 20 kilometers thicker than the near side. And nobody can fully explain why. Swirls painted across the surface that match no terrain. Quakes that ring the whole moon like a bell for an hour after a single impact. And the crew of Artemis 2 just brought back 7,000 new images. Scientists are already finding things in those photographs that do not match their models. Some of it is small, a shadow that falls the wrong way, a color shift across a Terminator line. 6 meteoroid impact flashes caught on camera during the flyby. Some of it is not small at all. Because when you zoom into those images and start measuring the terrain, a picture emerges that has been troubling lunar scientists for decades. The moon is not a dead rock orbiting Earth. The moon is a crime scene. And something happened here, long ago, that left evidence we are only now learning how to read. Start with the strangest clue of all. The moon is grey. Ask anyone. Look at any photograph taken from your backyard. Ash, chalk, charcoal, bone. Pick your shade. Grey. Except that is not what the crew of Artemis 2 saw. Glover was the first to say it out loud. Then Koch, then Wiseman. 4 trained astronauts, all in the same capsule, all looking through the same windows, all reporting the same thing to Houston. The moon has color. Soft browns, muted greens, warm tans across the highlands, and cooler shades sunk into the ancient lava plains. This is not a poetic flourish. Lunar scientists on the ground nearly cheered when they heard it, because for decades, high-precision telescopes and orbiting spacecraft have been mapping the moon's surface in wavelengths the human eye cannot see. they have known the color is there. They just did not know whether a person, with their own eyes pressed up against a capsule window, would actually be able to perceive it. The answer is yes. And the reason the color exists matters more than you might think. Here is what is happening. Every shade on the moon is a chemical fingerprint. The browns come from iron-rich minerals that erupted as lava billions of years ago and then cooled in the airless dark. The greens are trace amounts of olivine, a mineral that also forms deep inside our own planet. The creamy pale regions, the ancient highlands, are made of a mineral called anorthosite, light, aluminum-rich rock that floated to the top of a molten moon like scum on cooling soup. So when you look at the moon, you are not looking at a uniform ball of rock. You are looking at a map, a chemical autobiography. Different regions formed at different times, under different conditions, from different material. The colors are the handwriting. And the handwriting tells a story that does not add up. Because when scientists look at where the colors are, they find a pattern. The near side, the side we can see from Earth, is covered in dark brown and near black plains called Maria. The far side, the one the Artemis 2 crew just photographed in full, is almost completely drained of those dark plains. Only about 1% of the far side is mare. On the near side, it is 31%. Think about that gap. 31 to 1. 30 times more volcanic activity on one side of the same world. Why? Nobody has fully solved it. There are theories. There are computer models. There is evidence pointing in several directions at once. But the simple, honest, scientific answer is that the two hemispheres of the moon look like they belong to two different planets, and we do not yet know the exact sequence of events that produced that difference. What the crew saw through their windows was not just color. It was a visual record of something violent, something one-sided, something that happened to this moon in its infancy and never corrected itself. Koch leaned closer to her window. She described craters that glinted like broken glass, tiny pinpricks of light across a darkened surface, as if someone had poked thousands of holes in a lampshade and lit it from behind. That is not a metaphor. That is the next clue. A lampshade with tiny pinprick holes. That is the exact phrase Christina Koch used while flying past the moon at thousands of miles per hour. She was not describing the big craters, not Tycho, not Copernicus, not the dark basins you can see with binoculars from your backyard. She was describing something smaller, something her crewmates confirmed they were seeing too. Across the darkened regions of the moon's surface, at the boundary where sunlight meets shadow, there were bright little points. Hundreds of them, thousands, scattered randomly, each one glowing for no obvious reason. They were young craters, and they are a clue to how old the rest of the moon really is. Here is the science. When an asteroid slams into the lunar surface, it does not just dig a hole. It blasts a plume of bright, fresh rock outward in every direction. That fresh material is different from the surrounding terrain in one critical way. It has not been sitting exposed to space. Space does something brutal to lunar rock. The constant rain of micrometeorites grinds the surface into fine powder. Solar wind hammers every atom with charged particles. Ultraviolet radiation bleaches the chemistry. Over hundreds of millions of years, the surface darkens and dulls. Scientists call this process space weathering. So when you see a crater that is still bright, still standing out against the darker background, you are looking at something recent. Recent on cosmic timescales, anyway. Recent meaning anywhere from a few thousand to a few 100 million years old. Every pinprick Koch saw was a scar. Every one of them was a moment in time. An impact, a flash, a shower of debris, frozen permanently into the surface because the moon has no atmosphere to erase it. Earth erases its scars. Wind, rain, and living things smooth out craters in a geological eye blink. Volcanism paves over old terrain. Plate tectonics drags entire continents underground and melts them down. Our planet has been hit by asteroids just as often as the moon has. You just cannot see the evidence anymore. The moon keeps everything, every single impact, for 4.5 billion years. Imagine that for a second. You are looking at a surface that has recorded every violent event in its history with near-perfect fidelity. Every rock that ever hit it, every lava flow that ever spread across it, every tremor, every slump, every shift of the regolith, all of it preserved, the way a photograph preserves a face. And there is a problem. The Apollo missions brought back about 800 pounds of moon rock. Scientists dated those samples and built a timeline for the entire inner solar system. The number of craters of a certain size per square mile became a kind of clock. More craters meant older surface. Fewer craters meant younger surface. This clock was used to date Mars, Mercury, and every other airless body we have visited. The Artemis 2 images show hundreds of bright young craters that were not on previous high-resolution maps at the same densities. In some areas, more. In some areas, fewer. Scientists are now going to have to recalibrate the clock. And when you recalibrate the clock, you have to re-examine what is buried beneath the surface, because something down there does not make sense either. In the 1960s, Soviet and American engineers noticed something wrong with their spacecraft. Every time a probe orbited the moon and passed over certain regions, it would suddenly speed up, then slow down, then drift off course. The deviations were small but persistent, and they followed no pattern the engineers could predict. Some orbits shifted by 100 times more than the calculations said they should. Apollo planners called them navigational hazards, reefs in an ocean. You had to chart them and sail around them, because if you did not, your spacecraft would crash. And crash they did. 2 small satellites released during the Apollo 15 and 16 missions were sent into low lunar orbit. The teams on the ground had done their best to account for the bumps in the moon's gravity. Both satellites slammed into the surface anyway. The moon pulled them down. Something was down there. Something massive. Something that had no business existing where it did. Scientists gave it a name. They called it a mascon, short for mass concentration. A mascon is exactly what it sounds like, a concentrated lump of extra mass buried beneath the lunar surface. When a spacecraft flies over one, the extra pull yanks it slightly closer to the moon. When it flies past, the tug releases. Over many orbits, these little jolts add up until the orbit itself becomes unstable. Here is the part that confused everyone for decades. Mascons are not evenly distributed. They are concentrated in specific places. Specifically, they cluster under the huge dark basins on the moon's near side, the lava plains we have been talking about. Mare Imbrium, Mare Serenitatis, Mare Crisium, Mare Orientale. Now think about what that means. These basins are depressions, giant bowls carved out of the surface by ancient asteroid strikes. You would expect them to have less mass, not more. You scooped out a crater, right? Less rock should mean less gravity. But the opposite is true. The craters pull harder than the mountains around them. In 1998, NASA sent a mission called Lunar Prospector to map the gravity field in detail. It confirmed the weird result. Some flat, dark lava plains have stronger gravitational pull than the tallest highland peaks right next to them. The first explanation was that dense lava had pooled in the basins and filled them with heavy rock. That works for some of the basins. But other mascon basins have almost no lava fill, and they are still pulling too hard. The lava theory could not account for all of them. Something else was happening underground, something bigger than a lava flow. Then, in 2011, NASA launched 2 small spacecraft called Grail. Ebb and Flow, they flew in formation over the moon, measuring the distance between each other with laser precision. When one satellite dipped slightly because of a mascon below, the 2 spacecraft drifted a tiny bit closer or farther apart. That drift revealed the lumpy gravity of the entire moon at resolution never seen before. What Grail found was not a simple answer. It was a pattern, a shape. And when scientists traced the outline of that shape, they realized every major mascon on the moon had exactly the same buried structure. It looked like a bullseye. The Grail spacecraft drew maps no one had seen before. When scientists at MIT laid the data flat and studied the gravity around each mascon basin, a pattern jumped out. Every single one had the same structure, a center of extremely strong gravitational pull, a ring of weaker gravity wrapped around that center, then another ring of strong gravity outside that, a bullseye, carved in gravity. hidden under hundreds of miles of rock. Maria Zuber led the Grail mission. She said the pattern was so consistent, so precise, that it had to come from a specific kind of event, something that happened the same way every time. The team ran computer simulations. They modeled different impact scenarios, different rocks, different speeds, different angles. Only one scenario produced the bullseye. Picture an asteroid the size of a small city. It hits the moon at tens of thousands of miles per hour. In seconds, it excavates a crater hundreds of miles wide. Rock and dust fly outward, piling up in a dense ring at the crater's edge. This is the outer ring of the bullseye, a band of compressed heavy debris. But the impact is not finished. The shockwave plunges down into the moon. It hits the mantle below and rebounds, like a spring snapping back. Dense mantle rock, the heavy stuff that normally lies miles below the crust, gets dragged up toward the surface. It pools in the center of the crater. This becomes the inner bullseye, a dense plug of mantle material trapped near the top. Between the two rings, the crust is broken, fractured, less dense than either the center or the outer ring. That is the band of weaker gravity. Then everything cools. Over hundreds of millions of years, the molten rock hardens. The crust becomes strong again, rigid enough to hold the dense plug in place. The bullseye is frozen, and it stays frozen for 4 billion years. This is the part that should stop you cold. A bullseye gravity anomaly is not erosion. It is not drift. It is a permanent scar in the structure of the moon, a record of the exact moment of impact, preserved the way a bruise is preserved under the skin. Every time you look up at a full moon, the dark patches you can see are lava plains. But underneath each one is this buried bullseye, a dense heart at the center, a broken ring around it, an outer ring of debris, invisible from the surface, betrayed only by the way they tug on passing spacecraft. Zuber said something striking about this discovery. She said mascons tell us more about what happened to the ancient moon than almost anything else we can observe. The size of the central plug tells you how big the asteroid was. The width of the rings tells you how hot the moon's interior was at the time. The depth of the bullseye tells you how thin the crust was back then. Reading the bullseyes is like reading tree rings. Each one is a diary entry, and the entries are terrifying. They record a period of bombardment so intense it would have sterilized any planet in its path. Asteroids larger than any we see today. Impact energies equivalent to 1 trillion nuclear weapons. This is the part of the story no one likes to think about, because those same rocks were heading for Earth too. J. Melosh, the Purdue geophysicist who led key work on the mascons, once described them in a single phrase. He called them a real pain in the neck for Apollo planners, like reefs in an ocean, things to be avoided and planned around. That language is not a joke. Those mascons have been wrecking spacecraft for more than 50 years. Let's walk through what actually happens when a mascon gets hold of you. You are in a low lunar orbit, 50 miles up, give or take. Your velocity is fixed by physics. The moon's gravity pulls you inward. Your sideways motion carries you forward. The balance keeps you in a circle. If the gravity changes even a little, the balance breaks. Now you fly over Mare Imbrium. Beneath you, hidden under miles of ancient basalt, is a mascon. Its gravitational pull is noticeably stronger than the surrounding area. For the minute or two you are overhead, your spacecraft dips lower than it should. Just a little, maybe a mile, maybe less. You fly past. The pull weakens. You rise again. Now do it 100 times. 200. Every time you cross that mascon, you dip. Every time you leave it, you rise. But the dips are not symmetrical. The moon's gravity is lumpy enough and uneven enough that each pass shaves a tiny amount of your orbit's altitude. You are not going back up to quite where you started. After a few weeks, the low points of your orbit have dropped significantly. Maybe you are down to 30 miles, then 20, then 10. Then your spacecraft grazes a mountain range, or a ridge, or a crater rim. That is how the Apollo subsatellites crashed. Mission planners thought they had accounted for the lumpy gravity. They had not accounted for it enough. Both probes were slowly pulled to their deaths by mascons they could not see. Modern missions have solved this by flying at higher altitudes, or by using active propulsion to correct their orbits continuously. But even today, planning an extended low orbit around the moon requires massive computing power to simulate how the mascons will slowly tug on any given trajectory. A landing mission heading for the lunar South Pole has to calculate dozens of these gravitational twists before it ever fires an engine. Artemis 2 did not orbit the moon. It flew past, a free return trajectory that used the moon's gravity as a slingshot to swing integrity back toward Earth. The crew was never in low orbit, so the mascons never got a chance to pull the spacecraft down. But Artemis 3 and the missions that follow will orbit, and they will dock with landers. And the landers will descend. Every one of those maneuvers has to account for a gravitational field that behaves like a minefield. Here is the uncomfortable truth. We still do not have a complete map of every mascon on the moon. The far side was charted in detail only recently, and small anomalies, the kind that might nudge a lander by a few hundred feet during a descent, are still being catalogued. A precision landing on an unknown mascon could throw off a touchdown by enough to miss a safe zone entirely. The moon's hidden gravity is not ancient history. It is an operational problem for every future mission. And the bullseyes are only part of what is down there. The rest is far stranger. There is a layer buried inside the moon that glows, not with visible light, with radiation. Scientists call it KEREP. The letters stand for potassium, rare earth elements, and phosphorus. Those are the chemicals concentrated inside this mysterious layer, along with thorium and uranium, two of the most radioactive elements in the periodic table. KREEP is not spread evenly through the moon. It is not mixed into the crust like flour in a cake. It is concentrated, pooled, sitting in a specific region like spilled dye that refused to diffuse. And almost all of it is on the near side, the side we can see from Earth. Stop for a moment and consider that. Picture the moon floating in space. Split it down the middle. One hemisphere, the side facing us, carries an enriched load of heavy radioactive elements. The other hemisphere, the far side, has almost none. Scientists can measure this from orbit. The Lunar Prospector spacecraft mapped thorium across the entire surface in the late 1990s, and the map is almost cartoonishly lopsided. The near side glows on a thorium map like a spotlight. The far side is dark. How did this happen? The current best theory starts with a young, molten moon, a moon covered entirely in a global ocean of magma. That ocean cooled slowly. As it did, different minerals crystallized at different temperatures. The lightest ones floated to the top and formed the crust. The heaviest ones sank and formed the mantle, but the very last liquid to crystallize was a strange chemical left over. It had high concentrations of the elements that did not fit neatly into ordinary minerals: potassium, rare earths, phosphorus, thorium, uranium. These incompatible elements got squeezed out of everything else and ended up in a thin layer trapped between the crust and the mantle. That layer was creep. It should have wrapped around the entire moon, like frosting on a cake. It did not. Something happened that moved almost all of that creep onto one hemisphere, something that scooped it out of the far side and pushed it under the near side. And whatever that event was, it also explains why the near side is covered in volcanic plains and the far side is not. Because creep is radioactive. Radioactive elements generate heat, and heat generates magma. The near side has more creep, so the near side stays hot longer. A hot interior produces volcanic activity. Magma finds its way up through the crust and erupts onto the surface as lava flows. Those lava flows harden into the dark plains you can see from your backyard. The far side has almost no creep, so the far side cooled faster. Less heat, less magma, less volcanism, a quieter history, a less disturbed surface, a side that looks almost untouched compared to the near side. The thorium map and the volcanism map overlap almost perfectly. They are two faces of the same process. But this does not answer the real question. What moved the creep? What took a layer that should have been evenly distributed and shoved it onto one hemisphere? Scientists have been arguing about this for decades. The leading candidates all involve something spectacular: a dwarf planet slamming into one side of the young moon, an early second moon colliding and merging. An impact so colossal it rearranged the interior of an entire world. The best suspect so far is buried near the moon's south pole, and Artemis astronauts are headed straight for it. The map is almost embarrassing. Scientists call it the thorium distribution map of the moon. It comes from a gamma-ray spectrometer that flew on lunar prospector in the late 1990s. The instrument could detect the faint radiation leaking out of the lunar surface and measure how much thorium was present in any given patch of ground. When the finished map came back, it looked like someone had poured a bucket of radioactive paint onto one side of the moon and left the other side clean. The enriched region has a name. Scientists call it the Procellarum Creep Terrain. It covers a huge portion of the near side, centered roughly on the large dark plane called Oceanus Procellarum. Thorium concentrations there are several times higher than anywhere else on the moon. The far side thorium map, by contrast, is mostly cold blue, low values everywhere, with only a few faint patches of red. This asymmetry is not subtle. It is not a gradient. It is a line, and it extends beyond just thorium. Titanium, another metal, shows the same pattern. Near side, abundant. Far side, scarce. Iron does too, to a lesser degree. Even the chemical signatures of the rocks themselves are different. Apollo astronauts brought back basalts from the near side that were loaded with heavy elements. China's Chang'e 6 mission, which landed on the far side in 2024, brought back basalts with noticeably different chemistry. Different potassium isotopes, different iron isotopes, as if the two hemispheres had been cooked under different conditions at different temperatures for different lengths of time. Here is the deeper mystery. The moon should not be able to produce this kind of split on its own. Planets tend to mix themselves up. Convection currents in the mantle stir material around. Volcanism carries fresh rock from deep inside to the surface. Impacts churn the crust. Over billions of years, any chemical imbalance should smooth out. The longer a world exists, the more uniform it should become. The moon did the opposite. Whatever difference existed between its two sides, it locked it in place and preserved it for 4.5 billion years. The asymmetry is older than every rock you will ever find on Earth's surface. It is older than almost anything we can study directly. And it points to an event, not a process. A single moment in the moon's history that permanently scarred its chemistry into two distinct hemispheres. Scientists have narrowed the suspects down to a short list. A massive oblique impact on the far side that plowed through the crust. A merger with a smaller companion moon that plastered extra material onto one hemisphere. A collision with a wandering dwarf planet that rearranged the moon's insides. All the explosive consequences of the largest crater in the solar system, sitting right there on the far side. A scar so big you could drop the continental United States inside it, sideways. That last possibility is the strongest one, and it leads us to a place the Artemis program has made its primary target. A place that may hold the physical evidence of the event that split the moon in two. A place that was almost certainly formed by a rock the size of a small country. Luna 3 was a Soviet spacecraft. In October 1959, it swung around the far side of the moon and sent back the first photographs humans had ever seen of the hemisphere that faces permanently away from Earth. The images were grainy, barely more than shadows and suggestions, but they were enough to reveal something shocking. The far side looked nothing like the near side. Back home, every astronomer on Earth knew the moon's familiar face. The dark plains, the bright highlands, the features that formed the man-in-the-moon pattern generations had grown up watching. That face is a specific combination of two kinds of terrain. Bright cratered highlands make up about 69% of the near side. Dark, smooth lava plains called Maria make up the other 31%. When the far side images came back, the balance was gone. The far side was almost entirely cratered highland. Less than 2% of it was mare. It looked less like the moon we knew and more like the surface of Mercury, a battered ancient wasteland with no dark plains to break up the monotony of craters. This is the lunar dichotomy, the two-faced moon, and it has been one of the biggest unsolved problems in planetary science for 70 years. Artemis 2 gave us the sharpest look yet. The crew photographed huge sections of the far side during their 7-hour flyby on April 6th. One image, taken by Hansen through the spacecraft's second window, shows the heavily cratered terrain at the eastern edge of the South Pole Aitken Basin, with shadow pooling along the terminator. The texture is relentless. Crater on top of crater on top of crater. No smooth plains, no soft curves, just overlapping bowls of destruction going back 4 billion years. Compare that to the near side's Mare Imbrium. Flat, dark, smooth as a frozen lake. A basin that filled with lava and solidified into a nearly featureless plain, with only a scattering of newer impacts to break it up. 2 hemispheres, 1 world, radically different appearances. What is going on? The differences run deeper than what you can see from orbit. The Grail mission showed that the far side crust is, on average, about 20 kilometers thicker than the near side crust. In some places, the difference is closer to 50 kilometers. The far side also has more ancient crust exposed, less volcanic resurfacing, and fewer of the massive mass concentrations that dominate the near side. The far side is older looking, rougher, colder, more ancient. And here is the part that will bend your brain. When Grail measured the moon's internal temperature using gravity data, it found that the near side mantle is hotter than the far side mantle. Not by a little, by 100 to 200 degrees Celsius. The 2 hemispheres of the moon, right now, today, are at different internal temperatures. One is warmer than the other. It has been that way for billions of years, and the temperature difference is connected to the chemistry difference, which is connected to the crust thickness difference, which is connected to the volcanism difference, which is connected to the thorium distribution difference. Everything on the moon is asymmetric. The asymmetry is not one problem. It is the same problem expressed in a dozen different ways, and the source of that problem is buried somewhere in the moon's earliest history. The thickness of the far side crust is where the mystery gets physical. Take 2 maps of the moon. One shows the surface as you see it through a telescope. The other shows the thickness of the crust beneath every single point on that surface. The first map is familiar. The second map is where the trouble starts. Grail drew that second map. Its 2 spacecraft flew tight formation patterns over every part of the moon and measured the thickness of the crust by watching how the gravity changed. In some places, the crust turned out to be thin, about 20 kilometers, or roughly 12 miles. In other places, the crust was much thicker, 50 or 60 kilometers, maybe more in a few spots. The thin crust is almost entirely on the near side. The thick crust is almost entirely on the far side. The dividing line runs roughly along the boundary between the 2 hemispheres, give or take a few degrees. On average, the far side crust is about 20 kilometers thicker than the near side crust. That is a stack of rock, about the height of 20 Mount Everests, sitting permanently on one half of the moon and missing from the other. 20 kilometers. That is not a minor difference. That is the difference between a planet that can erupt easily and a planet that cannot. Magma has to push up through the crust to reach the surface. A thicker crust acts like a lid. A thinner crust is a doorway. This is the simplest explanation for why the near side has so many lava plains and the far side has almost none. The magma could punch through the near side. It could not punch through the far side. Even when huge impacts on the far side cracked the crust open, the lava flows were limited. Sometimes just a thin coating, sometimes almost nothing at all. The South Pole Aitken Basin is the best evidence of this. It is the largest, deepest confirmed impact on the moon. The impact was violent enough to excavate material from the mantle itself, and yet only 3 to 4% of the basin floor is covered in typical lava plains. The crust around it was so thick and had cooled so completely that the magma never made it up through in large quantities. So the thickness gap explains the volcanism gap. Good. But what explains the thickness gap? This is where scientists still disagree. The leading idea is that the near side of the young moon stayed hot longer than the far side. When the moon first formed, from debris blasted off Earth after a giant collision, Earth was still glowing hot from that same impact. The near side of the newborn moon was pointed directly at that glowing Earth and got baked by its heat. The far side was shielded from it. As the magma ocean began to crystallize, the far side cooled faster. Its crust formed first, at higher elevations. The near side stayed molten for longer. Its crust formed later at lower elevations. The difference in timing left the far side with a thicker, older crust and the near side with a thinner, younger one. That theory is elegant. It is also incomplete. Because a more recent scenario, one that gets stranger the closer you look, suggests the thickness difference was not just gradual cooling, it was a single catastrophic event, an impact from something almost as big as a small planet. And that something left evidence buried beneath the far side's surface. In 2019, a team of scientists led by Menghua Zhu at the Macau University of Science and Technology proposed something that sounds more like a disaster movie than a scientific theory. They suggested that the moon, not long after it formed, was struck by a wandering dwarf planet, not an asteroid, not a comet, a full-sized dwarf planet, roughly 480 miles across. Something a little smaller than the dwarf planet Ceres, which currently sits in the asteroid belt. This object, the theory says, was floating through the inner solar system on its own orbit. At some point, that orbit crossed paths with the young moon. The collision speed was around 14,000 miles per hour. Slow by asteroid standards, actually. Asteroids usually hit at 40,000 or more. But the impactor was so large that speed barely mattered. It hit the near side. Zhu's team ran computer simulations of what such an impact would do. The results were staggering. An object that size, hitting at that speed, would not just make a crater, it would shatter the whole hemisphere. It would also throw up an enormous volume of debris, crushed rock, vaporized minerals, molten material, that would arc around the moon on a short ballistic flight and come raining down on the opposite side, the far side. In the simulations, 3 to 6 miles of debris piled up on the far side after the impact. That extra layer of material would thicken the far side crust substantially. It would bury the original crust under a layer of impact ejecta. It would alter the chemistry of the surface, adding new elements and minerals that had originally been on the impactor or deep inside the moon. The thickness anomaly, the chemistry difference, the two-faced moon, all of it from a single catastrophic collision. This is still a theory. It is not proven. It competes with other theories, some of which are also quite strange. One alternative proposes that Earth once had 2 moons instead of 1. In the very early days, the 2 moons found themselves on orbits that eventually merged. The smaller moon slowly drifted toward the larger one, and, instead of a violent collision, landed softly on one side, plastering an extra layer of crust onto the hemisphere now known as the far side. Another theory argues that the dichotomy is older than either of those events. It says the chemical asymmetry already existed, baked into the moon at the moment of formation, and the volcanic differences cascaded from there. The single biggest impact on the far side, the one that created the South Pole Aitken Basin, then amplified the pre-existing asymmetry by heating one hemisphere more than the other. Scientists are not settled on which theory is correct. New data from Chang'e 6 on the far side's chemistry is giving weight to the South Pole Aitken heating hypothesis. But nothing has ruled out the dwarf planet collision, and some of the fine details of the crust still match that scenario better than any other. What all of these theories share is something unsettling. They all say the moon's current shape is not just the product of slow evolution. The moon was shaped by violence, specific, one-time, catastrophic events that rewrote its geography in a matter of minutes. One of those events left the largest crater in the solar system, and Artemis astronauts are about to land inside it. There is a hole in the moon so large it defies ordinary description. It is called the South Pole Aitken Basin. It sits on the far side, stretching from near the moon's south pole up toward the equator. It measures roughly 2,500 kilometers across. That is about 1,500 miles, wide enough to fit the continental United States inside it, if you laid the country on its side. It is nearly 8 miles deep at its lowest point. From rim to floor, the topography drops farther than the Grand Canyon is wide. If you could fly over it with the right lighting, you would see a gash in the lunar surface so vast that even from orbit it looks less like a crater and more like a wound. It is the largest, deepest, oldest confirmed impact structure on the moon. It is one of the largest impact structures anywhere in the solar system, rivaled only by a few ancient scars on Mars and Mercury. And it was made by a single event that happened around 4.25 billion years ago. Scientists do not know exactly how big the object was that made it. Models suggest something between 50 and 150 miles wide, a small asteroid by solar system standards, but still enough rock to make a continent on Earth. The impact speed was probably somewhere around 20,000 miles per hour. The energy released by that collision has been estimated as the equivalent of 1 trillion atomic bombs. Think about what that number actually means. The most powerful nuclear weapon ever detonated, the Tsar Bomba, released about 50 megatons of energy. The impact that made the South Pole Aitken Basin release roughly 20 billion times that. In less than a minute, the shock wave would have pulsed through the entire moon, rebounding off the far side and focusing back at the antipodal point on the opposite hemisphere. The antipode of SPA sits not coincidentally near Oceanus Procellarum, on the near side, the region with the most creep, the most thorium, the most volcanism. Scientists have been arguing for years about whether that is a coincidence or a clue. The current best theory says it is not a coincidence at all. The shock wave from SPA carried so much heat through the moon's mantle that it triggered hemisphere-scale convection. Dense, heat-producing material, including KREEP, got swept through the interior and concentrated on the near side. The volcanism we see on the near side today is the echo, billions of years later, of that one impact. A single rock, hitting in the right place at the right angle, may have permanently changed the moon's interior. The Artemis program has made SPA a top priority, not because it is dramatic, although it is, because the floor of SPA is the one place on the moon where you can possibly find material from the moon's deep interior sitting on the surface. The impact punched through the crust. Mantle rock was excavated and sprayed across the basin floor. If astronauts can collect those rocks, they could answer questions that have haunted planetary science for half a century. Artemis 4, currently targeted for early 2008, plans to land in exactly this region, specifically on the southern rim of the basin, near the moon's south pole. But to understand why that landing site matters so much, you have to understand something strange about the angle of the SPA impact. It came in sideways. Most craters in the solar system look like circles. That is because most impactors come in at steep angles, close to 90 degrees relative to the surface. A vertical strike produces a nearly perfect round hole, regardless of the direction the object was moving when it hit. The South Pole Aitken Basin is not round. When you look at it on a topographic map, it is elongated. It narrows toward the south. This is a classic sign of an oblique impact, a strike that came in at a low angle, maybe 20 or 30 degrees above horizontal, and slid across the surface, rather than drilling straight down. For years, scientists assumed the impactor came in from the south, based on the basin's orientation. In 2024, a team led by Jeff Andrews Hanna at the University of Arizona took another look. Their analysis suggested the opposite. The basin narrows southward, because that is where the impactor was heading when it hit. The collision actually came from the north, sliding southward across the lunar surface. That sounds like a minor distinction. It is not. An oblique impact does different things than a vertical one. Less of the kinetic energy gets converted into heat at the point of contact. More of it goes into stripping material off the surface and throwing it forward, downrange from the impact direction. That ejected material piles up asymmetrically around the basin. More debris on the downrange side, less on the uprange side. Andrews Hanna's team found exactly this pattern in the real data. On the western side of SPA, the ejector blanket is rich in radioactive thorium. On the eastern side, it is not. The radioactive material was excavated from deep inside the moon and then flung forward in a specific direction, matching a northward to southward impact trajectory. This is why the landing site matters. The downrange rim of SPA, the southern rim, where Artemis plans to land, should be piled high with material from the moon's deep interior, crust that was buried for 4 billion years, mantle rock that normally sits 20 miles below the surface, samples of creep material that were part of the original magma ocean layer. These are not rocks you can find anywhere else on the moon. They are not in the Apollo samples. They were not brought back by Chang'e. They exist in any quantity in exactly one place, and that place is where American astronauts are preparing to set their boots. There is more. The oblique nature of the impact means that the energy distribution was also asymmetric. A big chunk of the impact heat was delivered not straight down but sideways into the moon's mantle in a specific hemisphere. Simulations by a team that studied SPA in detail, published in the scientific journal Science Advances, showed that this asymmetric heating could explain the movement of creep material toward the near side over the following few 100 million years. The idea is that the heat wave from SPA set up a kind of convection current inside the moon. The current slowly dragged heat-producing elements across hemispheres and concentrated them on the opposite side, like stirring a pot and having all the sediment drift in one direction. If that theory is right, then the moon we see today is the product of a single oblique impact. One rock, hitting at the right angle, reshaped an entire world. Here is what computer simulations show happening when the South Pole Aitken impactor hit the far side of the moon. Time 0. The object, perhaps 100 miles across, makes contact with the surface. Because the angle is shallow, it does not embed itself immediately. It skips, it plows. For the first few seconds, it is more like a knife dragging across clay than a bullet hitting a wall. Time 5 seconds. A crater begins to open. The impactor is pushing an enormous wave of compressed rock forward and downward. The surface is vaporizing around the contact zone. Temperatures exceed 10,000 degrees Celsius. Time 1 minute. The crater has reached its maximum transient depth. In this instant, the hole in the moon is deeper than the current distance from Earth's surface to its mantle. The moon's crust has been punched through. Mantle rock is exposed. Time 10 minutes. The transient crater begins to collapse. Walls slump inward. The floor of the basin rebounds upward, like a water droplet hitting a pond and creating a temporary central peak. Impact melt pools across the basin floor. Time 1 hour. Debris from the impact has reached the opposite side of the moon. Some of it is vaporized rock that has traveled nearly the full circumference and is now raining down on the antipodal region. Some is slower ejecta that is still in flight. The entire moon is ringing from the shockwave. Time 1 day. The surface has begun to freeze over. The lava that filled the transient crater is solidifying. The central rebound peak is collapsing under its own weight, but the real effects are only just beginning, deep below. Time 100 million years. The heat from the impact is still distributing itself through the mantle. A team of researchers at the University of Arizona and other institutions simulated this stage in detail. They showed that the SPA heat pulse would have set up a slow convection current in the moon's interior. Hot mantle rock would have moved away from the impact region. Cooler mantle rock would have moved in to replace it. The currents were hemisphere scale. Time 500 million years. The convection has dragged the remnants of the magma ocean's last layer, the creep material, across the moon's interior and concentrated it on the hemisphere opposite the SPA impact. That hemisphere is the near side. Time 1 billion years. The creep, now concentrated on the near side, is generating so much radioactive heat that the mantle beneath the near side is still melting. That melting produces the magma that erupts through the thinner near side crust and forms the Maria. The moon's face is being drawn. Time 2 billion years. Most of the major volcanism is over. The near side looks roughly like the moon we know today. Time 4 billion years. We look up from Earth. We see the man in the moon, not knowing that every one of his dark patches exists because of a single impact on the other side. 4 billion years ago. This sequence is still under active investigation. Not every detail is confirmed, but each new piece of evidence, the thorium asymmetry, the crust thickness difference, the mantle temperature gap, is consistent with it. The moon in this picture is not a passive world. It is a survivor, and the internal heat gradient that one ancient impact left behind is still measurable today. The moon has a fever, only on one side. Grayle's gravity measurements did more than map crust thickness. They also allowed scientists to model what is happening inside the moon right now, in the present. By combining gravity data with measurements of how the moon flexes under Earth's tidal pull, researchers calculated something remarkable. The mantle beneath the near side is measurably warmer than the mantle beneath the far side. The estimated difference is between 100 and 200 degrees Celsius, 200 to nearly 400 degrees Fahrenheit. That is a lot. Think about what that implies. Heat does not stay still. If you put a hot object next to a cold object, the heat flows. Over 4 billion years, any temperature difference inside a rocky body should have smoothed itself out. The fact that the moon is still maintaining this gradient after all this time means something is actively producing heat on one side. That something is creep. The near side's concentration of thorium and uranium is generating measurable radioactive decay heat. Those elements release energy as they decay into lighter elements over billions of years. Enough of them, concentrated in a specific region, can keep that region noticeably warmer than everywhere else. The temperature difference is not just a curiosity. It has real physical consequences. A warmer mantle is a softer mantle. A softer mantle is easier to melt. A softer mantle convects more actively, producing more volcanism. The whole near side is in a sense a hotter, more geologically active hemisphere even today. The far side, by contrast, has cooled more completely. Its mantle is stiffer. Its crust is thicker. Its volcanic activity ended much earlier in the moon's history. When you look at a Chang'e 6 far side basalt, you are looking at volcanism that stopped sooner than near-side volcanism did. Now connect this to what Artemis 2 observed. The crew reported that the near side looked warm in color tones, browns, greens, rich dark patches of basalt. The far side looked colder, grayer, heavily textured with crater shadows and overlapping impacts. Those visual impressions are not wrong. They reflect a real underlying thermal difference between the two hemispheres, expressed through 4 billion years of geological activity. This has consequences for future lunar missions. A base near the warmer near-side mantle might sit on ground with slightly different thermal properties. Ground temperatures vary, drilling depths vary, the behavior of buried ice deposits varies. All of it matters when you are trying to build infrastructure on a world with no atmosphere and temperatures that swing from 250 degrees Fahrenheit in sunlight to negative 250 in shadow. Here is the part that should make you pause. The moon's interior is not in equilibrium. 4.5 billion years after it formed, it is still working through the consequences of events from its first few hundred million. The thermal gradient, the chemical asymmetry, the crust thickness mismatch. Everything we see, every feature on the surface, every difference between the two faces, is the slow unwinding of an ancient catastrophe. And sometimes, that unwinding produces effects we can still detect in real time, like moonquakes. The Apollo seismometers recorded them for years after the astronauts left. And what they recorded was impossible. Apollo astronauts left instruments on the moon, seismometers, small devices designed to listen for vibrations in the lunar ground. The seismometers listened for years, and what they recorded stunned the scientists back on Earth. When something struck the moon, a meteoroid, a discarded rocket stage, anything, the surface did not behave the way Earth's surface does. On Earth, a large impact sets off a sharp shock that fades quickly. Minutes, not more. Because Earth's crust is wet, fractured, and layered with soft sediments that absorb vibrations. The moon is dry. It has no water to damp the ringing. Its crust is ancient, cold, and cracked into a chaotic rubble pile from billions of years of impacts. When a vibration starts, it does not get absorbed. It bounces. It scatters. It rings. After an impact, the moon can vibrate for nearly an hour. Scientists described it, memorably, as ringing like a bell. That phrase has been picked up by conspiracy theorists over the years to suggest the moon is hollow or artificial. It is neither. The ringing is fully explained by the moon's unique physical properties. A dry, cracked, seismically efficient body conducts vibrations in a way that planets with atmospheres and oceans simply cannot. The Apollo seismometers detected several kinds of moonquakes. Some were tidal, caused by Earth's gravity stretching the moon as it orbits. These happen regularly, almost on a predictable schedule, as the moon reaches certain points in its orbit. They are deep, hundreds of miles below the surface. Other quakes were shallower. These were not on a schedule. They happened unpredictably, and they were strong. Some of them, scientists estimated, would have been capable of destroying a human settlement if any had been standing above them. Shallow moonquakes are the ones that worry mission planners for future bases. They are not tidal, they are something else, and for decades, the exact cause was unclear. Then, in 2019, a team of researchers using data from NASA's Lunar Reconnaissance Orbiter proposed an answer. They found that shallow moonquakes were happening near features called lobate scarps. These are cliff-like ridges scattered across the lunar surface, typically 100 to 300 feet high. The scarps are young, geologically speaking. Some are less than 50 million years old. A few may still be forming right now. And they are forming because the moon is shrinking. The lunar interior is slowly cooling. As it cools, it contracts. The crust, which is already brittle and ancient, cannot stretch to accommodate the shrinkage. Instead, it breaks. Slabs of crust slide over each other, creating thrust faults that push sections of surface upward. Those upward pushes create the lobate scarps, and they also generate quakes. The moon is not dead. It is shrinking, actively, today, measurably. Artemis 3 and later missions plan to land near the lunar South Pole, which is, unfortunately, a region with many lobate scarps and a high rate of shallow seismic activity. A moonquake during a landing operation, or during habitat construction, would be a genuine problem. The Apollo astronauts walked on a moon they thought was dead. We now know it is not. It is trembling, it is ringing, it is contracting, and the activity is not slowing down in any meaningful way on human timescales. Which raises a question. If the moon is still shrinking, how much has it shrunk, and what does a shrinking world leave behind? You cannot see it from Earth with your own eyes, but the moon has wrinkles, thousands of them, long curving cliffs scattered across the surface, some hundreds of miles in length. They are called lobate scarps. They look, in high-resolution orbital photographs, like the wrinkles on a drying piece of fruit, or the creases that form on an apple left in a bowl for too long. The comparison is not just poetic, it is literal. The moon is drying out, not in water, in heat. A world the size of the moon, once molten and glowing, slowly loses its internal heat over billions of years. As the interior cools, it contracts. A cooler sphere has less volume than a hotter sphere. The core shrinks, the mantle shrinks. The crust, which is the thin outermost layer, has to follow. But a crust is not elastic. It cannot just stretch or compress smoothly. It is brittle. When it is forced to fit a smaller surface area, something has to give. So the crust cracks, and sections of it slide over other sections. Where the sliding meets the surface, you get a cliff, a thrust fault, a lobate scarp. These scarps were first noticed in detail by the Lunar Reconnaissance Orbiter in the late 2010s. The orbiter's high-resolution cameras mapped thousands of them across the moon. Some are short, less than a mile long. Some stretch for hundreds of miles. Nearly all of them have the same distinctive curve. Scientists estimated that, since the ancient past, the moon has shrunk by something like 150 feet in radius. That sounds like nothing compared to the moon's total size. It is not nothing. Spread that contraction across the entire surface, and you get enough stress to fracture the crust in thousands of places. And the scarps are still forming. Evidence of recent activity is everywhere. Boulders perched precariously on scarp faces. Fresh-looking fault lines with sharp edges that have not been rounded by space weathering. Small, shallow moonquakes clustered around specific scarp locations, recorded by the Apollo seismometers before their batteries finally died. Some of those quakes were significant. One, detected in the Taurus-Littrow Valley near where Apollo 17 landed, would have registered around 5 on the Richter scale if it had happened on Earth. A magnitude 5 quake is not catastrophic, but it is strong enough to damage buildings that were not designed for it. A future lunar habitat, sitting on dusty regolith a few hundred feet from an active lobate scarp, would not take a magnitude 5 hit gracefully. Standard habitat designs do not include seismic bracing. They would need to. This is why the Artemis program is studying the moon's surface in such detail before any crewed landing. Every scarp near a potential landing site has to be mapped. Every one has to be evaluated for activity. The South Pole region, where Artemis 4 is targeted, has numerous scarps. Some of them are suspected to be active. Here is what matters about all of this. The moon is not a museum piece. It is an active world, changing on human-relevant timescales. A wrinkled surface, a shrinking interior, a quaking crust. These are not historical footnotes. They are ongoing processes that will shape every future lunar base, every future mission, every future human presence on that world. And the wrinkles are only the beginning of what is changing. Because in some regions of the moon, the surface itself is behaving in ways that should not be possible at all. Look at a high-resolution photograph of a region called Rhina Gamma. It sits on the near side of the moon, in the middle of a large lava plain. It is one of the strangest features in the entire solar system. It looks like someone took a paintbrush soaked in cream and drew a looping curling pattern across a dark floor. Bright lines twist and curl in shapes that have no connection to the terrain beneath them. They do not match craters. They do not match mountains. They do not match any topographic feature at all. They just sit there, painted on the surface, as if the moon had been decorated. These features are called lunar swirls. Rhina Gamma is the most famous, but there are dozens scattered across the moon. Some are small. Some stretch across miles of terrain. All of them have the same basic property. They are bright, looping patterns that appear to float free of the landscape. For a long time, scientists had no idea what they were. The swirls were reported in Earth-based telescope photographs going back decades. Up close, orbiting spacecraft confirmed they were real features, not optical tricks. But their origin was unclear. Then scientists noticed something. Every swirl sits on top of a magnetic anomaly. The moon as a whole has no global magnetic field. It does not have the kind of liquid iron core that generates the protective magnetic shield Earth relies on. But in specific localized regions of the lunar surface, the rock itself is magnetized. These are ancient magnetic fields, frozen into the crust billions of years ago, and preserved ever since. Every lunar swirl corresponds to one of these magnetic patches, every single one. The current best theory is that the magnetic field above each swirl acts as a shield. Solar wind, the constant stream of charged particles blowing outward from our star, normally bombards the lunar surface and slowly darkens it over time. This is one of the main processes behind space weathering. Where the surface is shielded from solar wind, it stays brighter. Where it is not shielded, it darkens. The swirls, under this theory, are the bright footprints of invisible magnetic umbrellas. The rock beneath them has been protected from the constant battering of charged particles for billions of years. The darker terrain surrounding each swirl has not. This theory has a lot of evidence supporting it. Spacecraft measurements show that charged particles really do get deflected around swirl regions. The patterns of brightness really do match the patterns of magnetic field strength. But it is not a complete answer. Nobody knows why the magnetic anomalies are where they are. Nobody knows why some regions got magnetized while others did not. Nobody knows why the magnetic patches have the specific shapes they do. Shapes that produce curling, looping patterns on the surface. Some scientists have proposed that ancient impacts created brief bursts of magnetic field that became locked into the cooling rock. Others have suggested that the magnetic anomalies are the buried remains of ancient dynamo cores that formed early in the moon's history. Still others think dust transport by electrostatic forces might play a role, pushing fine particles around and enhancing the brightness contrast. There is no consensus. The swirls remain, in some ways, as mysterious as they were when telescope astronomers first noticed them. Which brings us to the bigger question: where did these magnetic patches come from in the first place? The answer involves a moon that once had something it has since lost. Take a compass to the moon. Point it around. It will not do much of anything useful. The moon does not have a global magnetic field. Whatever direction you face, the needle has nothing to align with. This is one of the most basic differences between the moon and Earth. Our planet's magnetic field protects us from cosmic radiation, shapes our auroras, and drives the behavior of charged particles in the upper atmosphere. The moon has none of that. But take a rock sample from the Apollo missions back to a laboratory on Earth. Put it under sensitive instruments, and some of those rocks are magnetized. Not weakly. Some lunar rocks carry magnetic signatures strong enough that, 4.5 billion years ago, They must have formed in a magnetic field comparable in strength to Earth's. This is a problem, because the Moon, as far as anyone can tell, cannot generate that kind of field today. It does not have the right internal structure. Its core is too small, and if there is any liquid iron in it, the volume is nowhere near enough to drive a dynamo like Earth's. So where did the magnetism come from? Scientists have been working on this for decades. The leading theory is that the ancient Moon, when it was young and hot, did have a dynamo. A small liquid iron core at its center may have churned in a way that generated a magnetic field. That field, while it existed, magnetized the rocks that were crystallizing on the surface. The field then died. Eventually, the core cooled enough that the liquid iron solidified or slowed too much to produce a dynamo. The global field collapsed, but the magnetized rocks stayed magnetized. They became fossils. Every lunar magnetic anomaly on the surface today is one of these fossils, a frozen snapshot of a field that stopped existing billions of years ago. That theory has a problem too. The math does not quite work. To produce the magnetic field strengths measured in Apollo samples, the ancient Moon would have needed a dynamo stronger than any theoretical model easily allows. The core is just too small to have driven such a powerful field under ordinary conditions. So a second theory has emerged. What if the magnetic field was not continuous? What if it flickered on and off, driven by external events? The proposal is this. Big impacts on the lunar surface might have briefly amplified weak magnetic fields. The impact plasma, a cloud of superheated charged particles, can generate its own temporary field. If that field happened to coincide with a moment when molten rock was cooling and locking in its magnetic orientation, the result would be a preserved magnetic signature in the crust. Under this theory, each strongly magnetized region on the Moon corresponds to an ancient impact event. The swirls mark the places where the Moon was hit, briefly magnetized by the shockwave, and then cooled down while still inside the magnetic pulse. Neither theory is confirmed. The Artemis program is expected to bring back new samples that will test both theories against fresh evidence. A rock from a swirl region, returned with its orientation preserved, would tell scientists more about how the magnetism formed than anything we currently have. But the deeper question is not just whether the Moon had a magnetic field. It is whether the Moon's interior is still capable of generating one, and recent evidence suggests it might be, just barely. Deep inside the Moon, roughly 1,000 miles below the surface, there is a core. For a long time, nobody was sure what it was made of, or how big it was, or whether any part of it was still liquid. The Moon is too small to maintain much internal heat. Most of its primordial heat should have radiated away billions of years ago, leaving a solid, cold core all the way through. In 2011, a team led by Renee Weber at NASA reanalyzed the old Apollo seismic data using modern processing techniques. They found something that had been buried in the noise for decades: clear signatures of a lunar core with multiple layers, a solid inner core similar to Earth's, an outer core that was liquid, also similar to Earth's, and a partially molten boundary layer between the outer core and the mantle. The liquid outer core was small, about 200 miles in radius, but it was there. This was a major discovery. It meant the Moon was more Earth-like in its internal structure than previously thought, and it meant that a lunar dynamo producing a magnetic field was physically possible in the ancient past. More recent analyses have added new details. In 2023, a study led by Arthur Briord at the French National Center for Scientific Research used precise measurements of the Moon's orientation over time to constrain the density of the core. The team concluded that the inner core is likely solid and made of something close to pure iron, with a radius of about 125 miles. The outer core, still liquid, surrounds it. If the outer core is still liquid today, and if there is any convection happening inside it, then the Moon might, just might, be capable of generating a very weak magnetic field in the present. Not a strong one, not anything like what the ancient Moon produced, but something detectable with the right instruments. Artemis missions are expected to deploy modern magnetometers on the lunar surface. These will be far more sensitive than anything Apollo left behind. If there is a present-day field, these instruments should be able to detect it. Imagine what that would mean. A world thought to be magnetically dead still faintly alive at its core. The heart not quite stopped, just slowed almost to silence. There is another piece of evidence worth considering. The moon's core also produces heat. That heat has to go somewhere. Most of it rises into the mantle and eventually escapes through the surface. But a small amount of it may still be melting rock at the core mantle boundary, producing tiny quantities of magma that never reach the surface. This buried magma could, in principle, explain some of the unexplained thermal anomalies detected by various orbital missions. Small, deep regions where the moon seems slightly warmer than expected. A lunar interior that is mostly cold, mostly frozen, but with a liquid heart still spinning faintly at its center. A world technically alive. Technically, this kind of internal activity matters for another reason too. Because beneath the surface of the moon, there is evidence of volcanic water. Not on the surface, hidden inside specific kinds of rocks, and the discovery of that water changed everything about how we understand lunar history. For most of the 20th century, every textbook said the same thing: the moon is dry. Completely, absolutely, totally dry. This was not a guess. It was a conclusion drawn from Apollo samples. Scientists had studied those rocks under the best instruments available and found no water. None. The moon's formation theory depended on this dryness. The giant impact that created the moon was supposedly so hot and so violent that any water would have boiled away and escaped to space before the moon could even cool into a solid body. Then, in 2008, a team led by Alberto Sal at Brown University re-examined some of the Apollo samples using new, more sensitive instruments. They found water inside tiny volcanic glass beads. The beads were small, about the size of grains of sand. They had formed billions of years ago, when ancient volcanic eruptions on the moon shot droplets of molten rock into the lunar sky. Those droplets cooled quickly in the airless environment and froze into glass before hitting the ground. The glass trapped whatever volatile chemicals had been dissolved in the magma at the moment of eruption. Inside the beads, preserved for over 3 billion years, was water. Not much, a few hundred parts per million by weight, but undeniably real. And the water chemistry matched water found inside volcanic rocks on Earth, suggesting a common origin. This discovery overturned the textbook. The moon is not completely dry. Its interior contains water, not lakes or rivers or puddles, but trace amounts of H2O locked inside rocks and beads and mineral crystal structures, probably distributed through the mantle in significant quantities. If the glass beads are representative, the moon's mantle may contain anywhere from tens to hundreds of parts per million water by weight. That may not sound impressive, but multiplied over the entire volume of the lunar mantle, it adds up to something real. Enough water to fill a small ocean in principle, if it could all be extracted. It cannot be extracted, of course. It is locked inside rocks distributed across an entire world. But its existence forces scientists to rewrite the history of the moon's formation. If the giant impact that made the moon was as hot as previous models suggested, water should not exist anywhere inside it today. The fact that it does exist suggests one of two things. Either the impact was less hot than the standard model, and some water survived the initial chaos, or water was delivered to the moon after it had cooled, perhaps by comets and asteroids that rained down during the heavy bombardment period of the early solar system. Both possibilities have serious implications. The first would require rewriting models of how the moon formed. The second would suggest that water delivery to rocky worlds is more common than we thought, and would change how we think about the origin of water on Earth. There is a twist. Chang'e 6, the Chinese mission that landed on the far side of the moon in 2024, brought back samples from the basin floor inside the South Pole Aitken Basin. Those samples were also analyzed for water content. The result was unexpected. Samples from the near side of the moon, brought back by Apollo and other missions, contained detectable amounts of water. Trace amounts, locked inside volcanic minerals and glass beads, but detectable. Samples from the far side, brought back by Chang'e 6, contain even less. The Chang'e 6 mission landed inside the South Pole Aitken Basin in June 2204. It was the first mission to return samples from the far side of the moon. The rocks it brought back were immediately valuable. ancient basalts from the floor of the largest impact basin on the moon, never before studied in a laboratory. When Chinese scientists analyzed the water content in those rocks, they found values significantly lower than near-side samples. The far-side mantle, based on this limited data, appears to be drier than the near-side mantle. This adds one more asymmetry to the list. The moon is chemically split down the middle. The near side has more creep, more thorium, more titanium, more volcanic activity, warmer mantle temperatures, and, apparently, more water. The far side has less of everything. Why would the water be asymmetric? The leading theory connects it back to the South Pole Aitken Basin impact. The heat from that event, the one that may have driven hemisphere-scale mantle convection, may also have driven water-rich material toward the near side. Water, when heated above certain temperatures, becomes mobile. It migrates through rock. Over the course of the post-impact convection cycles that lasted hundreds of millions of years, water would have moved alongside the creep material and ended up concentrated under the near side. The far side, having lost its volatile content in the initial impact event and never regained it through post-impact migration, stayed dry. If this theory is right, it means the moon's water distribution is another legacy of the same ancient catastrophe that produced everything else. One event, one impact, 4 billion years ago, and the consequences are still being measured in rocks handed back from the far side in 2004. There is one more piece of evidence that complicates the picture. Permanently shadowed craters near the lunar poles contain frozen water ice. These craters have been in eternal shadow for billions of years, never warmed by sunlight, and anything that drifted in, water from comets, water from volcanic outgassing, water from solar wind interactions, got locked in as ice. This polar ice is different from the water inside mantle rocks. It is surface ice. It is accessible. A future lunar base could in principle mine it for drinking water and rocket fuel. Artemis missions are targeting the South Pole specifically because of this ice. But the ice is complicated too. Its exact distribution is still being mapped. Its purity varies. Some craters may contain extensive ice deposits. Others, which looked promising from orbit, may turn out to have much less than expected. And the ice itself may be mixed with dust, other chemicals, and regolith in ways that will make extraction challenging. Still, the moon has water. It has more water than any textbook written before the year 2010 would have predicted. And the distribution of that water tells us yet another piece of the ancient story. Water is not the only thing showing up where it shouldn't. Light is too. For hundreds of years, astronomers have reported seeing strange flashes on the moon. Tiny bursts of light, sometimes reddish, sometimes bright white, sometimes faintly colored glows that appear, last for a few seconds or minutes, and then disappear. They happen in specific regions of the moon, certain craters, certain highland areas, and they have been seen by enough observers, across enough centuries, that the phenomenon cannot be dismissed as observational error. These are called transient lunar phenomena, TLPs for short. The earliest recorded TLP dates back to the 11th century, when a group of medieval monks reported seeing a bright flash on the moon. More recent sightings have come from astronomers using powerful telescopes, and even from spacecraft instruments. The database of TLP reports contains thousands of entries going back 400 years. What is causing them? Several explanations have been proposed. Some TLPs are almost certainly meteoroid impacts, rocks slamming into the moon at high speed and producing brief flashes of thermal radiation as the impact vaporizes the projectile. We know these happen regularly. Modern automated cameras have recorded dozens of confirmed lunar impact flashes over the past few decades, and spacecraft in lunar orbit have imaged their fresh craters afterward. But not all TLPs match the profile of impacts. Some last too long. Some change color in ways impacts do not. Some appear in specific geographic regions too often to be explained by random meteoroid strikes. One leading alternative theory is outgassing. The moon's interior may still be releasing trace amounts of gas through cracks in the crust. Radon, carbon dioxide, or other volatiles that have been trapped underground for billions of years may occasionally escape in small bursts. When these gases reach the surface, they can disturb the dust in the regolith, stirring up a temporary cloud that catches sunlight in a specific way. The cloud then settles, and the flash disappears. Another theory invokes electrostatic effects. The lunar surface charges up under solar radiation, and when the charge reaches certain thresholds, fine dust particles can levitate briefly above the surface. These floating dust clouds could scatter light in ways that produce observable flashes or glows. A region called Aristarchus is the most famous TLP hotspot. This crater and the surrounding plateau have generated more TLP reports than any other area on the Moon. Aristarchus is also unusually bright in normal conditions. The floor of the crater is composed of highly reflective material, and it sits on a geologically complex region that includes ancient volcanic features. Some scientists suspect the area may still be releasing small amounts of gas from subsurface reservoirs. The Artemis II crew, during their lunar flyby, was asked to watch for any unusual flashes. NASA had set up a citizen science program, encouraging Earth-based observers to do the same. The hope was that if amateur astronomers spotted a TLP, the crew could potentially observe it from orbit and confirm it. No TLPs were conclusively observed during the mission, but the crew did see something else, something more straightforward, but still significant. They saw 6 meteoroid impact flashes. During the 7-hour lunar flyby, while Integrity was passing over the Moon and the crew was focused on observing the surface, they saw 6 bright points of light appear briefly on the darkened side of the lunar surface. Each one was a meteoroid impact. Meteoroids hit the Moon constantly, without an atmosphere to burn them up. Every pebble and rock on a Moon-crossing orbit eventually slams into the surface at tens of thousands of miles per hour. These impacts release flashes of light bright enough to be seen from space, and sometimes even from Earth with sensitive cameras. The Artemis II crew was the first human team to watch this happen from up close. They reported the flashes in real time to mission control. NASA's science team on the ground cross-referenced the observations with Earth-based reports from the Citizen Science program. Some of the flashes may match impacts recorded by automated monitoring systems on Earth. Think about what this means. 6 impacts in just a 7-hour window on the hemisphere the crew was observing. If you extrapolate, the Moon is being hit by visible meteoroids somewhere on its surface dozens of times a day, every year, for billions of years. Each impact is small. Most meteoroids that produce visible flashes are only a few inches across. But the cumulative effect is significant. Over geological time, these impacts slowly rework the surface, grind rocks into dust, and deposit fresh crater scars onto otherwise ancient terrain. This is also a real hazard for any future lunar base. A direct hit on a habitat by even a small meteoroid would be catastrophic. Standard spacecraft hull designs assume some protection against micrometeoroids, but those designs were developed for short-duration missions, not permanent structures. A lunar base will need better shielding, possibly including buried modules or regolith-covered roofs. The flashes Artemis II saw were a reminder. The Moon is not a calm place. It is being bombarded, continuously, by debris left over from the formation of the solar system. We don't notice, because we're far away and the Moon is big enough to absorb most of what it receives. But up close, from orbit, the activity is visible. There is another aspect to the flashes that is only now being understood. The distribution of impacts is not perfectly even. Certain regions of the Moon get hit more often than others, depending on their orientation relative to Earth's orbit, the direction of meteoroid streams passing through the inner solar system, and the local gravitational environment. Scientists are using Artemis II's observations to improve models of this distribution. Future missions will need accurate maps of impact probability in order to choose landing sites and base locations with reasonable safety margins, and the flashes aren't the only thing the crew saw that was brief and spectacular. Just a few minutes after emerging from behind the far side of the Moon, as communication with Earth was re-established, Integrity passed into the Moon's shadow relative to the Sun. What they saw next had never been witnessed by human eyes before. From space, the geometry of a solar eclipse is different than it is from Earth. On Earth, a total solar eclipse happens when the Moon passes directly between the Sun and our planet, briefly blocking the Sun's disk. It is a rare event, visible only along a narrow path on the ground. and it typically lasts only a few minutes. Integrity was in a different position. It was on the far side of the moon, with the moon between itself and the sun. From the spacecraft's perspective, the moon appeared much larger than it does from Earth, close enough to fill most of the sky. When the sun aligned behind the lunar disk, the crew experienced a total solar eclipse that lasted for nearly 54 minutes. 54 minutes. Compare that to an Earth-based eclipse where totality lasts only a few minutes at best. The crew had brought solar viewing glasses. They put them on and watched. As the sun disappeared behind the moon, the outermost layer of the sun's atmosphere, the corona, became visible as a glowing halo around the dark lunar disk. The corona is normally invisible because the sun's brightness washes it out. Only during an eclipse can it be seen directly. But what the crew saw was even stranger than a typical corona. In the photographs they took, there is a broad, diffuse glow extending well beyond the sun's normal corona. Bright points of light are visible around the edges of the moon. Scientists on Earth, analyzing the images, identified those points as planets, Venus, Mars, and possibly Saturn, appearing as bright stars in the darkened sky. The diffuse glow raised questions. Part of it is corona, but part of it may be something else. Zodiacal light, perhaps. Sunlight scattered by dust particles along the plane of the solar system, or a combination of effects. The science team is still analyzing the images to figure out exactly what produced the glow. What matters for the moon story is what this unique vantage point revealed about the lunar surface during the eclipse. With the sun blocked, the only light reaching the near side of the moon came from reflection off Earth shine. This faint illumination let the crew see features on the dark side of the moon that would normally be completely invisible. Earth shine is about 10,000 times dimmer than direct sunlight. In eclipse conditions, it was the dominant source of light on the side of the moon facing away from the sun. And because Earth was fully illuminated from the moon's perspective, the Earth shine was slightly bluish, giving the near side of the moon a subtle blue tint in the eclipse photographs. This is not just an aesthetic observation. The color of Earth shine contains information about Earth's atmosphere, cloud cover, and surface conditions. Future missions may use lunar-based telescopes to study Earth shine in detail, as a proxy for understanding exoplanets, distant Earth-like worlds around other stars, whose reflected light contains similar chemical fingerprints. For 54 minutes, the crew of Artemis 2 watched a solar eclipse unlike any ever seen before. And the photographs they took may end up informing not just lunar science, but the search for life on other worlds. But one more thing about those eclipse images has scientists scratching their heads. NASA released the Artemis 2 eclipse photographs on April 7th. Almost immediately, analysts started arguing about one specific feature. Around the dark disk of the moon during totality, there is a glowing halo. That glow extends farther out from the moon than a typical solar corona should, and it has a slightly different texture than scientists expected. Two explanations are competing. The first explanation is the straightforward one. The glow is the solar corona, the sun's outer atmosphere, visible because the moon has blocked the sun's main disk. The corona has complex structure, with streamers, loops, and filaments extending outward from the sun's surface. Seen from the unique vantage point of a spacecraft, the corona might just look a little different than it does from Earth. The second explanation is stranger. Some of the glow might be zodiacal light. Zodiacal light is a faint glow produced by sunlight scattering off dust particles spread throughout the solar system. The dust comes from comets shedding material as they orbit the sun, and from collisions between asteroids. These particles form a thin disk aligned with the plane of the solar system, and sunlight reflecting off them produces a soft glow visible in dark skies from Earth, typically just after sunset or before sunrise. From the moon's far side during an eclipse, the zodiacal dust would have been brightly illuminated by sunlight coming from behind the lunar disk. The combination of corona and zodiacal light could produce exactly the kind of diffuse halo the Artemis 2 photographs show. NASA's science team is still working on disentangling the two contributions. The images have enough resolution to tell the difference, but the analysis takes time. Why does this matter? Because zodiacal light is interesting in its own right. The amount of dust in the inner solar system is not constant. It changes over time as comets shed new material and existing dust gets swept up by planets or pushed outward by solar radiation. Measuring zodiacal light accurately tells us about the current state of the dust population. More importantly, precise zodiacal light measurements are critical for future astronomy. Space-based telescopes trying to image faint, distant galaxies or detect exoplanets have to account for the dust glow as background noise. Better data means cleaner images. There is also a purely scientific curiosity at work. The Artemis 2 images are the first high-quality photographs ever taken of a solar eclipse from beyond the moon. Every subsequent crewed mission that goes near the moon during an alignment with the sun will have the opportunity to repeat this observation. Over time, a library of eclipse photographs from different positions in space will build up, giving scientists unprecedented three-dimensional information about the solar corona and the dust in our neighborhood. Here is what has some astronomers quietly excited. The faint glow extending from the moon during the eclipse is in a part of the sky normally so bright it is impossible to study from Earth. The sun's light, even scattered through Earth's atmosphere, washes out almost everything near the sun. Space-based eclipse observations from a spacecraft that can position itself exactly where the moon blocks the sun open up a window on the sun's neighborhood that we have barely begun to explore. Under that unfamiliar halo, the moon itself was hiding other secrets underground. In 2017, Japanese scientists using radar data from a probe called Kaguya announced something unexpected. Beneath a specific area of the lunar surface, in a region called Mare Tranquillitatis, where Apollo 11 landed in 1969, they had detected a massive underground cavity, an empty space, or near empty space, buried about 100 feet below the surface. The cavity was enormous, roughly 30 miles long and 60 miles wide, tall enough to fit skyscrapers inside it. It is a lava tube. Lava tubes form when a river of molten rock flows beneath a hardened crust. As long as the lava keeps flowing, the crust remains in place. When the lava eventually drains away or stops flowing, the crust is left behind as the roof of an empty tunnel. Lava tubes exist on Earth. Hawaii has many of them, but they are usually small, a few tens of feet across at most. Earth's gravity and geology keep them from getting much bigger. The moon has lower gravity and different geology. Lunar lava tubes can be enormous. Theoretical models had predicted they should exist in sizes far beyond anything on Earth, but Kaguya's discovery was the first direct confirmation. The Mare Tranquillitatis lava tube is not the only one. Other surveys have identified additional candidate cavities scattered across the lunar surface. Some are smaller, some may be even larger. The full catalogue is still being compiled. Why does this matter? Because a lava tube is, in principle, a ready-made shelter. Building a habitat on the lunar surface is hard. The surface is bombarded by micrometeoroids, cooked by unfiltered solar radiation, and exposed to temperature swings of over 400 degrees Fahrenheit between lunar day and night. Any surface habitat has to be shielded against all of this, which typically means burying it or covering it with thick layers of regolith. A natural lava tube solves most of these problems. The rock roof overhead provides radiation shielding, blocks meteoroid impacts, and stabilizes the internal temperature. Instead of building a shelter from scratch, you just move in. NASA and various private space companies have studied lava tubes as candidate sites for long-term lunar bases. The logistics are complicated. You have to find a tube with stable geology, a safe entrance, and access to other resources like water, ice, and sunlight for power. But the potential is real. There is a deeper implication too. If lava tubes can survive intact on the moon for billions of years, they might preserve ancient material in conditions never exposed to the harsh lunar surface environment. Samples from deep inside a lunar lava tube could include pristine ancient rock that has never been weathered by solar wind, micrometeoroids, or cosmic radiation. These samples would be invaluable for understanding the moon's earliest history. And there is something even more speculative. Some scientists have wondered whether lava tubes, sealed off from the surface for geological time, might have preserved ancient volatiles like water or organic molecules. The interior of a large lunar lava tube has not been directly explored. Whatever is in there has been sitting, undisturbed, since the tube formed billions of years ago. Artemis missions are not scheduled to visit a lava tube directly. But future missions, possibly including robotic explorers, dropped into tube entrances, could be some of the most scientifically interesting operations humanity undertakes on the moon. From caves hidden in the crust to craters hidden in permanent darkness, the moon keeps its most interesting secrets in places where light cannot reach. Near the lunar poles, there are craters that have never seen sunlight. The moon's axis is tilted only about 1.5 degrees relative to its orbit around the sun. That is an extremely small tilt compared to Earth's 23.5 degrees. The practical consequence is that at the moon's poles, the sun never rises very high above the horizon. In some polar craters, the sun does not rise at all. Deep crater floors remain in permanent shadow for billions of years. These are called permanently shadowed regions, or PSRs. Temperatures inside a PSR can drop as low as -400 degrees Fahrenheit. That is close to the coldest naturally occurring temperatures anywhere in the solar system. At those temperatures, any volatile compound that drifts into a PSR gets frozen solid and stays frozen. There is no warmth to melt it, no sunlight to sublimate it, no atmosphere to move it. Whatever falls in, stays. Over billions of years, PSRs have accumulated water ice, carbon dioxide, ammonia, methane, and a host of other frozen compounds. They are cold traps, chemical archives preserving material from comet impacts, solar wind interactions, and ancient lunar outgassing events. The lunar South Pole, where Artemis 3 and Artemis 4 are planning to land, is surrounded by PSRs. Some of these craters are thought to contain significant deposits of water ice, tens or hundreds of millions of tons of frozen water, accessible with the right drilling and extraction technology. Water is the most critical resource for any sustained lunar presence. It can be used for drinking, for growing food, and, most importantly, it can be split into hydrogen and oxygen for rocket fuel. A lunar base with access to water becomes a launching point for missions deeper into the solar system. Fuel produced on the moon is far cheaper than fuel launched from Earth, because you do not have to carry it up out of Earth's deep gravity well. This is why the South Pole matters so much. It is not just scenic, it is strategic. But the South Pole is also challenging. The permanent shadows that preserve the ice also make the terrain difficult. Temperatures inside PSRs will destroy most standard electronics. Drilling operations have to deal with a rock that has been frozen at near absolute zero for billions of years, and the landscape itself is rough: craters, ridges, scarps, and rubble piles, making it hard to find a flat, safe landing site with access to both sunlight for power and shadow for ice. Artemis is targeting landing sites near, but not inside PSRs. The idea is to land somewhere with good solar illumination, then drive or walk to nearby shadowed craters to extract ice. The PSRs have other mysteries too. Instruments on orbiting spacecraft have detected unusual reflectivity in some shadowed craters, suggesting that the ice there might be more than just a thin frost. It could be substantial sheets or layers. Some models suggest that certain PSRs might contain ice deposits dozens of feet thick in places. Nobody knows for sure, because nobody has looked directly. The robotic missions that have attempted to sample PSRs have either failed or returned only limited data. A crude mission, with proper instruments and the time to do careful science, could transform our understanding of these frozen tombs of ancient material. And the chemistry of the regolith around those poles? Also weird, because like everything else on the moon, it is asymmetric. Among the many chemical asymmetries of the moon, one of the most striking involves titanium. Apollo astronauts brought back a wide variety of rocks from the near side of the moon. When scientists analyzed them, they discovered that some of the lunar basalts were extraordinarily rich in titanium. Titanium levels in certain Apollo samples were several times higher than anything found in typical Earth rocks. When scientists looked for titanium on the far side, using orbital gamma ray and spectrometer data, they found almost none. The high titanium rocks were concentrated almost entirely on the near side. Specifically, they were clustered near the same regions where creep and thorium were also concentrated. Yet another asymmetry. The explanation ties back to the magma ocean. When the young moon's global magma ocean was crystallizing, different minerals solidified at different temperatures. Lighter minerals floated up, and formed the crust. Heavier minerals sank and formed the mantle. The very last things to crystallize were specific dense minerals, including one called ilmenite, an iron titanium oxide. Ilmenite is dense. It should have sunk, but the layer it formed in was also rich in creep and other heat-producing elements, which were trying to float up. The result was a complicated struggle between different densities and compositions in the last liquid layer of the magma ocean. Current theories suggest that this dense, titanium-rich, keep-bearing layer was gravitationally unstable. It wanted to sink, but the crust above it was a barrier. Over hundreds of millions of years, the layer began to destabilize. Parts of it sank, parts of it moved sideways. And here is the crucial part. The South Pole Aitken impact may have catalyzed the movement. When SPA hit, the heat pulse from the impact energized the layer. The dense, titanium-rich material began to flow. It drifted toward the side of the moon opposite the SPA impact, the near side. There it pooled, forming the concentrated deposits we see today as high titanium basalts. This process, called overturn by scientists who study it, may explain several observations at once: the titanium asymmetry, the KEREEP asymmetry, the near side's extra heat, the excess near side volcanism, all cascading from the single initial imbalance set up by the SPA impact. The Artemis program is interested in titanium for practical reasons too. Titanium and its compounds can be used in manufacturing and potentially in producing oxygen from lunar regolith. A base located in a high titanium region has different resource options than a base in a low titanium region. It also turns out that lunar titanium may have a very specific industrial use. Scientists have proposed that fine-grained titanium oxide can be used as a reactive ingredient for extracting oxygen from lunar soil. This process, called molten regolith electrolysis, is being developed as a way to produce breathable air and rocket propellant without shipping supplies from Earth. A lunar base on a high titanium plane could, in theory, manufacture its own oxygen from the ground beneath it. The moon's asymmetric chemistry, once purely a scientific puzzle, has suddenly become an economic asset. There is still a deeper layer to the puzzle, because the titanium didn't just tell us about the moon's surface, it told us something about its core. For decades, the composition of the moon's core was mostly a guess. The core is small, about 300 miles in total radius, divided into a solid inner core and a liquid outer core. But that is a tiny fraction of the moon's total volume. It sits about 1,000 miles below the surface. Nobody has ever directly sampled it. All we have are inferences from how the moon wobbles, how seismic waves travel through its interior, and how its gravity field is structured. Still, inferences can be powerful. Multiple independent measurements have converged on similar conclusions about the core's composition. It is primarily iron. It has small amounts of sulfur, nickel, and possibly some carbon, and it may have trace elements that match, oddly, the composition of certain asteroids that passed through the early solar system. Here is where the titanium clue becomes relevant. If the moon formed primarily from material ejected off Earth during a giant impact, its overall bulk chemistry should closely match Earth's mantle, and in many respects it does. But in some respects, like the unusually high titanium content on the near side, and some isotope ratios in the mantle, the moon looks slightly different from Earth. Recent analyses suggest that the moon's interior may have inherited some material from the impactor itself. Theia, the hypothetical Mars-sized body that hit the early Earth, would have contributed a significant fraction of the moon's mass. If Theia's chemistry was different from Earth's, those differences would show up as subtle compositional quirks in the resulting moon. The iron in the moon's core may be a direct inheritance from Theia. Theia's own iron core, torn apart in the giant impact, could have ended up distributed across both Earth and Moon, with some fraction sinking to the moon's center as the new world cooled. If true, this means the moon's heart is, in part, made of the corpse of another planet. That is a strange thought. Every beating magnetic field, every pulse of internal heat, every signature of a liquid outer core traces back to a vanished world that no longer exists as anything except fragments and memory. There is one more twist. Briot's 2023 analysis found that the lunar core density is consistent with a composition that is denser than pure iron alone. There may be some extra nickel and other heavy elements mixed in, consistent with iron meteorite chemistry. This matches the theory that the core contains ancient material from a differentiated parent body. The Artemis program hopes to deploy sensitive seismometers on the lunar surface. Data from those instruments will let scientists measure how seismic waves pass through the lunar core, constraining its composition more precisely than any previous mission could. Over the next decade, our picture of the moon's deepest interior should sharpen considerably. Until then, we know this. The moon has a heart. It is mostly iron. It is partly liquid. It may contain material from a vanished world. And it is still generating, deep below the surface, traces of the heat and motion that once made the young moon an active, magnetized body. Most of that activity is ancient, but some of it, just enough of it, might still be happening right now. One scar on the moon's surface seems to have recorded it all. On the western limb of the moon, straddling the boundary between the near side and the far side, there is a feature that astronomers have been photographing for centuries. From Earth, it appears as a dark, oval patch with a visible raised ring around it. Up close, it is one of the most spectacular impact structures in the solar system. Its name is the Oriental Basin. It is roughly 930 miles across. It was formed by an asteroid impact about 3.8 billion years ago. That makes it younger than the South Pole Aitken Basin, and in many ways better preserved. When you look at Oriental, you are looking at what SPA might have looked like shortly after it formed, before billions of years of subsequent impacts and volcanic activity had obscured its original structure. Oriental has a unique feature that few other basins preserve as clearly: multiple concentric rings. From the outside in, you can count 3 major rings: a broad outer ring about 900 miles in diameter, a middle ring at about 600 miles, and an inner ring at about 300 miles. These rings were not carved directly by the impactor. They formed in the minutes and hours after the impact, as the crust and mantle responded to the shockwave. Each ring marks a boundary where the lunar interior deformed in a specific way, where rock slumped, where the mantle rebounded, where the crust split and shifted. The Grail mission measured Oriental's gravity in fine detail. What it found was revealing. The basin's central region has a positive gravity anomaly, a Mascon bullseye, consistent with dense mantle material excavated during the impact. But the rings around it also have gravity signatures, and the pattern matches what computer simulations predict for a large impact on a specific type of crust. Specifically, the data suggest that the moon's crust beneath Oriental was at the time of the impact thinner and warmer than the global average. The impactor punched through easily. The mantle rebounded sharply, and the rings formed as the crust tried to settle back into a stable configuration, but could not quite manage it. Those rings are the moon's scar trying not to heal. 4 billion years later, Oriental is still not fully settled. Small gravity anomalies at the rings suggest that the basin's structure is still under strain, still adjusting very slowly to the immense stress of its ancient formation. Some of the shallow moonquakes recorded in the region may be related to this ongoing slow adjustment. Artemis II crew members observed Oriental during their flyby. They captured some of the first detailed close-up images of the basin from a human-crewed spacecraft in over 50 years. The photographs show the ring structure clearly, concentric mountain chains rising from the basin floor, casting long shadows in the low-angle sunlight at the terminator. Koch and her crewmates reportedly spent significant time observing Oriental. The basin was one of 30 specific science targets chosen for the mission. It remains one of the most scientifically rich features on the moon, a well-preserved laboratory for understanding how huge impacts shape planetary surfaces. And it is only one of the many things the Artemis II images will force scientists to re-examine, because the data from this mission is going to take years to fully process, and what they find in it may rewrite parts of the lunar story entirely. 7,000. That is the number of photographs the Artemis II crew captured during their 10-day mission. Most of those images have not yet been released to the public. NASA has shared a selection of the most visually striking ones, but the scientific analysis of the full dataset is only beginning. Over the coming months and years, lunar scientists will work through each photograph in detail, comparing features to existing maps, identifying new details, and hunting for anything that does not match current models. Some of what they find will be small, a boulder in the wrong place, a subtle color shift across a terminator boundary, a slightly sharper crater rim than expected. Some of it will be bigger. The crew captured high-resolution images of regions on the far side that have never been photographed in this level of detail before. They observed areas under specific lighting conditions, low-angle sunlight at the terminator, that reveal topographic features invisible in full daylight. They documented color variations, texture differences, and subtle brightness patterns that Earth-based telescopes cannot resolve. A few specific science questions are already being addressed by the new data. First, the lunar crater size and age distribution. The crew's photos will help refine the existing crater count database, potentially revising our estimates for how quickly the lunar surface has been bombarded over various time periods. This in turn affects our understanding of Earth's impact history and the timing of major events in the early solar system. Second, the distribution of lunar swirls on the far side. Previous orbital data had identified many swirl features, but Artemis 2's photographs provide visible light context that complements the instrumental data. Scientists can now correlate observed brightness patterns with the magnetic anomalies they sit on, potentially improving models of how the swirls form. Third, the fine structure of the South Pole Aitken Basin. The crew observed the eastern edge of SPA from a unique vantage point and captured details of ejecta patterns that will help refine models of the impact geometry. This matters for planning the Artemis 4 landing site. Fourth, the current state of the lunar terminator. The boundary between lunar day and night is constantly moving, and observing it at high resolution lets scientists study how sunlight interacts with rough topography, how shadows behave on regolith, and how the lunar surface thermally responds to the transition between light and dark. Fifth, the appearance of the moon from the human eye's perspective. Previous missions used optimized instruments, not human vision. The subjective observations of 4 trained astronauts, the brown and green hues they reported, the lampshade effect, the visual brightness of specific features, will inform how future missions design their visual interfaces, their displays, and their astronaut training. There will almost certainly be surprises. Historical missions have a track record of revealing features nobody expected. Apollo found glass spherules with water. Lunar Prospector found the creep asymmetry. Grail found the Mascon bullseyes. Chang'e 6 found the far side chemistry differences. Artemis 2 will add to this list. What, specifically, we do not yet know. But we know the moon does not give up its secrets willingly. Every mission reveals new mysteries at the same time it solves old ones. And the next missions are already being planned. Artemis 2 was not the end. It was the beginning. The mission's primary goal was to test the Orion spacecraft and the Space Launch System rocket, with a crew on board. It was about validating systems, practicing procedures, and proving that humans could once again travel beyond low Earth orbit and return home safely. By that measure, the mission was a success. Integrity performed well. The crew survived. The data came back. But the deeper goal is to return humans to the lunar surface. That is what Artemis 3 and Artemis 4 are designed to do. Artemis 3, currently scheduled for 2027, will be a more modest mission. After concerns about the heat shield and delays with the Starship lunar lander, NASA revised the plan. Artemis 3 will now launch to low Earth orbit to practice rendezvous and docking with a commercial spacecraft. It will not land on the moon itself. That is a practical step back, meant to reduce risk. Artemis IV, targeted for early 2028, is the mission that returns humans to the lunar surface. It will land near the moon's south pole, in a region selected for its access to permanent shadow, for water ice, and permanent sunlight, for solar power. The landing site sits on the southern rim of the South Pole Aitken Basin, the downrange rim of the largest impact structure on the moon. The place where, if the oblique impact theory is right, the deepest ejected material from the lunar interior should be piled up. If the astronauts find what scientists hope they will find, they will collect samples containing mantle rock, They will find traces of the ancient creep layer. They will bring back fragments of the very material that shaped the moon's chemistry and drove its two-faced asymmetry. They will, in effect, sample the moment of the crime. The Artemis program is planned to continue beyond that. Additional missions will establish a more permanent presence. A lunar base called Artemis Base Camp is under development. A lunar terrain vehicle is being designed. Spacesuits capable of long-duration surface operations are being tested. International partners including Canada, Europe, and Japan are contributing components, astronauts, and scientific instruments. The moon in 2040 will look very different from the moon in 2026. There will be infrastructure on its surface. There will be regular cargo deliveries. There will, barring further delays, be humans living and working on it for months at a time. And all of it will be built on top of a world we still do not fully understand. The lopsided crust, the asymmetric chemistry, the magnetic ghost of a dead dynamo, the bullseye gravity anomalies, the swirls that shouldn't exist, the moonquakes that ring for an hour, the wrinkles in the shrinking crust, the cave systems hidden underground, the water frozen in shadow, the glass beads that carry mantle water, the titanium hiding on only one side. Every one of these is a chapter in a story that began 4.5 billion years ago and is still being written today. Artemis 2 saw the moon with human eyes for the first time in over 50 years. The crew came back with 7,000 photographs, 4 pairs of wide-open eyes, and a better understanding of what we do not yet know. The moon is hiding something, multiple somethings, and the next generation of missions is going to drag those secrets into the light. The silence at the edge of the far side, those 40 minutes when 4 astronauts lost contact with Earth, was the sound of humanity listening for the first time in half a century. We are going back. And this time, we plan to stay long enough to hear what the moon has been trying to tell us. Thank you for staying with us. See you on the next one.